Tonight, we're going to talk about the silence. Not the silence in your room right now, not the quiet between songs. The silence of the universe itself. And when you truly understand the scale of what's out there, that silence stops being ordinary. It becomes one of the strangest and most troubling facts in all of science. Start with the numbers. The observable universe stretches roughly 93 billion light-years across. Inside that volume, astronomers estimate there are at least 200 billion galaxies. Each of those galaxies contains billions of stars. Some contain hundreds of billions. The Milky Way alone holds somewhere between 200 and 400 billion stars, and most of those stars have planets. Not some of them. Most of them. Studies over the last 2 decades have made that clear. Planets are not rare. They are the default. Of all those planets, astronomers estimate that billions sit within what we call the habitable zone, close enough to their star to have liquid water on the surface. Not too hot, not too cold. The right temperature range for chemistry to get complicated, for oceans to form, for something to crawl out of those oceans. Now think about what that means mathematically. If only 1 in a million of those habitable planets ever developed life, the number of life-bearing worlds in the observable universe alone runs into the hundreds of trillions. If only 1 in a million of those went on to develop intelligence, you still end up with hundreds of millions of civilizations. Civilizations that built tools, that looked up at the sky, that wondered what was out there, that started broadcasting signals into space. The universe, by the math, should be full of them. And yet, when we point our instruments at the sky, when we listen across every frequency we know how to detect, when we scan billions of stars looking for any signal, any pattern, anything that could not have come from a rock or a gas cloud, we find nothing. Not a faint whisper, not an ambiguous blip we can't explain, nothing that has ever held up. The universe is silent. That silence has a name. Most scientists call it the Fermi Paradox. It traces back to a summer afternoon in 1950 at Los Alamos National Laboratory in New Mexico. Enrico Fermi, one of the most prominent physicists of the 20th century, was having lunch with a group of colleagues. They had been talking casually about the possibility of extraterrestrial life. The conversation had moved on to other things when Fermi suddenly asked, almost offhandedly, "Where is everybody?" 3 words. That was the whole question. Where is everybody? His colleagues understood immediately what he meant. If the universe is as vast and as old as it appears, if the conditions for life are as common as they seem, then civilizations should exist. Many of them. Some of them should be millions or billions of years more advanced than we are. A civilization even 1,000,000 years older than humanity would have had time to develop technologies we cannot imagine. They would have had time to spread across their entire galaxy, to build structures detectable from light years away, to fill the cosmos with the evidence of their existence. And we see none of it. Not a single confirmed signal, not a structure, not a pattern in the stars that someone put there on purpose. The universe looks, in every direction we examine, like a place where nothing intelligent has ever existed except us. Most people, when they first hear this, assume there must be a simple answer. Space is big, they say. Maybe the signals just haven't reached us yet. Maybe other civilizations are too far away. But that reasoning breaks down when you actually run the numbers. The Milky Way galaxy is about 100,000 light-years across. A civilization that developed spacefaring technology even 1,000,000 years ago would have had time to visit every star system in the galaxy many times over, even at a tiny fraction of the speed of light. The age of the universe is 13.8 billion years. There has been time. more than enough time. So the question Fermi asked at that lunch table in 1950 was not really a casual one. It was pointing at a genuine gap between what the math predicts and what we actually observe. A gap that has never been satisfactorily closed. A gap that has generated decades of serious scientific work and produced no consensus answer. What we are left with is the silence itself. That strange, vast, unyielding quiet that sits between the stars and refuses to resolve into anything meaningful. Physicists study it. Astronomers listen for breaks in it. Philosophers argue about what it implies for our place in the cosmos. The silence is either telling us that we are alone in a universe too large to comprehend, or it is telling us something about what happens to civilizations that reach our level of development. Both possibilities are genuinely difficult to sit with. There are explanations, there are theories, some of them quite serious, some of them deeply unsettling. And the more carefully you think about it, the more unsettling the answer becomes. Let's start with the numbers, because the numbers are what make this so hard to dismiss. The Milky Way galaxy contains somewhere between 200 and 400 billion stars. That range alone is difficult to hold in your mind. Astronomers can't count them individually. The estimate comes from measuring the galaxy's total mass and light output and working backward. Even at the low end, 200 billion is a number with no real equivalent in everyday experience. If you counted one star per second without stopping, it would take over 6,000 years to reach 200 billion. Now consider that most of those stars have planets. This wasn't always known. For most of human history, we had no direct evidence that other stars had planets at all. That changed in the 1990s when astronomers began detecting planets orbiting other stars using indirect methods. Since then, the data has been overwhelming. Surveys suggest that on average, every star in the galaxy has at least one planet. Some have several. The total number of planets in the Milky Way likely exceeds 1 trillion. Of those, astronomers estimate that somewhere between 10 and 40 billion orbit within the habitable zone of their star. The habitable zone is the range of distances where liquid water could exist on a planet's surface. Not guaranteed, just possible. Rocky planets in that zone are the category we're most interested in. Conservative estimates put the number of rocky, potentially habitable worlds in our galaxy at several billion. That's not the universe. That's just our galaxy. In 1961, an astronomer named Frank Drake developed a mathematical framework for thinking through all of this. The Drake equation isn't a calculation in the traditional sense. It's a way of organizing the problem. It takes the rate of star formation in the galaxy, multiplies it by the fraction of stars with planets, then by the number of planets per star that could support life, then by the fraction that actually develop life, then by the fraction of those where intelligence emerges, then by the fraction that develop technology capable of communication, and finally by the average length of time such a civilization remains detectable. Multiply those values together, and you get an estimate of how many communicating civilizations exist in the Milky Way right now. Most of those variables are uncertain. Some are deeply uncertain. Drake's original estimate produced a number around 10 civilizations currently broadcasting in our galaxy. Other scientists running the same equation with different assumptions have gotten numbers ranging from less than 1 to millions. The range is enormous because the uncertainty is enormous. But here's what matters. Even under conservative assumptions, the math keeps producing civilizations. Drive every variable as low as you reasonably can, and the equation still tends to output something greater than zero. Think about what that means. If only 1 in a million planets in the habitable zone ever develops life, that's still thousands of worlds with life in our galaxy alone. If only 1 in a million of those develops technological intelligence, that's still a number that isn't zero. And our galaxy is just one of more than 200 billion galaxies in the observable universe. The scale multiplies in every direction you look. There's another dimension to this that most people don't fully sit with. The universe is 13.8 billion years old. Earth is 4.6 billion years old. Life appeared on Earth within the first billion years. Intelligent, technological life appeared only in the last few 100,000 years. That means other planets with a head start of even a few 100 million years would have civilizations that are hundreds of millions of years more advanced than we are. A civilization 1,000,000 years more advanced than humanity would be almost incomprehensible to us. We've had radio for about 150 years. We've had spaceflight for less than a century. In 1,000,000 years, assuming we survived and continued to develop, our technology would bear no resemblance to what exists today. Now imagine a species that has been doing this for 100 million years, or 1,000,000,000. Whatever that looks like, it would appear to us as something indistinguishable from the laws of physics themselves. And crucially, civilizations with that kind of head start would have had time to spread. Our galaxy is roughly 100,000 light years across. Even at a small fraction of the speed of light, a civilization with millions of years to work with could have colonized every star system in the Milky Way many times over. This is what makes the silence so hard to explain. It's not just that we'd expect to hear a radio signal from somewhere. We'd expect the entire galaxy to show signs of engineering, megastructures, modified star systems, patterns in the cosmic background that don't fit natural explanations. We see none of that. None. The physicist Enrico Fermi reportedly captured this in a single question during a lunch conversation in 1950. The people around the table had been discussing the probability of intelligent life elsewhere in the universe. Fermi looked up and asked essentially, "Where is everybody?" Not as a formal scientific paper, not as a calculated challenge, just a question at a lunch table. But the question has never been answered, and it has never gone away, because the math behind it doesn't go away. The question has spawned decades of serious scientific inquiry. Astronomers and physicists have proposed countless hypotheses to resolve the paradox. Some have suggested that intelligent life might emerge and destroy itself through nuclear war or environmental collapse before reaching the point where it broadcasts into space. Others have wondered if the universe operates under communication protocols we haven't discovered. Some researchers have proposed that perhaps any civilization sufficiently advanced chooses not to communicate, or that they operate on timescales and through methods entirely foreign to our understanding. The search continues, driven by the fundamental puzzle that Fermi posed so casually. What we're left with is a gap between what the numbers predict and what we actually observe. The numbers say the galaxy should be full. Our instruments say it isn't. Those two things cannot both be true in the straightforward way we initially assume. Either the numbers are wrong in ways we don't understand, meaning life and intelligence are far rarer than probability suggests, or our instruments and methods are missing something fundamental, or something is systematically preventing civilizations from reaching the point where we detect them. Those are genuinely different categories of explanation, and they lead to very different conclusions about our place in the universe. Something is wrong with the picture, and there are really only a few ways it can be wrong. Since 1960, astronomers have been pointing radio telescopes at the sky and waiting. That was the year Frank Drake aimed the Green Bank telescope in West Virginia at two nearby stars and listened for signals. He heard nothing unusual, but the effort launched something much larger. It became the foundation of SETI, the Search for Extraterrestrial Intelligence, a scientific program that has been running in various forms for more than 6 decades. The basic idea is straightforward. If a civilization somewhere out there has technology comparable to ours or beyond it, they might be broadcasting radio waves. Radio travels at the speed of light. It passes through space with relatively little interference. It's detectable across enormous distances. If you wanted to announce your existence to the rest of the galaxy, radio is a reasonable way to do it. So astronomers built bigger telescopes, developed more sensitive receivers, and started scanning the sky across millions of different frequencies. Projects multiplied, equipment improved. Computing power allowed researchers to analyze data that would have been impossible to process in earlier decades. The effort became genuinely serious. And in all that time, across all those frequencies, across decades of listening, the result has been essentially nothing. No repeating signal. No structured pattern that couldn't be explained by a natural source. No confirmation of any kind that something out there was trying to communicate. Scientists have detected plenty of interesting natural phenomena. Pulsars, quasars, fast radio bursts from distant galaxies. The universe is not radio silent in any simple sense. It's full of noise. But none of that noise has ever resolved into something that looked deliberate. Nothing has ever looked like a message. There is one exception, and most people who follow this subject know exactly which one it is. On August 15, 1977, an astronomer named Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University. He noticed a signal that stood out from everything around it. It was strong. It was narrow in frequency. It lasted for 72 seconds, which was exactly as long as the telescope's field of view allowed. The signal matched almost perfectly what scientists had predicted an extraterrestrial transmission might look like. Amon circled it on the printout and wrote a single word in the margin. Wow. The name stuck. That signal became known as the Wow Signal, and it has never been satisfactorily explained. More importantly, it has never been detected again. Dozens of follow-up observations pointed at the same region of sky, at the same frequency. Nothing. Whatever produced it, whether it was natural, artificial, or something in between, it appeared once and vanished. The Wow signal is the closest thing SETI has ever found to a genuine candidate, and it remains unexplained after nearly 50 years. Most scientists are careful about what they conclude from this. The absence of a signal is not proof that nothing is out there. That point deserves to be understood clearly. SETI has surveyed only a small fraction of the sky. The searches have covered a limited range of frequencies relative to the full electromagnetic spectrum. The telescopes used have mostly looked at one narrow slice of the sky at a time. The total effort, impressive as it is by human standards, amounts to something like checking a few glasses of water from an ocean and concluding the ocean contains no fish. The search has barely started. But here's what makes the silence significant despite that limitation. The galaxy is old. It has had billions of years for civilizations to develop. A civilization just a few thousand years more advanced than us would have communication technology we probably can't imagine. A civilization a million years ahead of us might have the capability to broadcast signals powerful enough to reach every corner of the Milky Way without difficulty. If even a handful of civilizations in our galaxy reached that level and chose to broadcast for any length of time, the signals should be detectable. They should be hard to miss. The math from the previous section suggested there could be thousands of technological civilizations in the galaxy right now. If any of them were transmitting at anything like the power levels an advanced civilization could reasonably achieve, SETI should have found something by now. Instead, the sky is quiet, and that quietness is itself a data point. Some researchers argue that we simply haven't looked long enough or hard enough. Projects like Breakthrough Listen, launched in 2015 with substantial funding, have pushed the search further than anything before it. They've surveyed more stars, covered more frequencies, and processed more data than the previous 5 decades combined. The results so far have been the same: natural signals, interesting astronomical objects, and no confirmed evidence of intelligence. Others point out that our search strategies carry assumptions that might be wrong. We look for radio signals because radio is what we know how to use. An advanced civilization might have moved past radio communication entirely, switching to technologies we haven't developed yet and couldn't detect even if we were pointed directly at them. That's a real possibility. But it doesn't fully resolve the problem, because a civilization advanced enough to abandon radio would presumably also be advanced enough to leave other kinds of traces: large-scale engineering, altered stellar spectra, waste heat from massive industrial processes. We've looked for some of these things too. Nothing confirmed. The picture that emerges after 60-plus years of searching is uncomfortable. Not definitive. Nobody responsible is claiming proof of anything. But uncomfortable. The universe had every opportunity to answer. We built the instruments. We pointed them at the sky. We waited. The silence, after all these years and all that effort, is deafening. The simplest answer to Fermi's question is the most uncomfortable one. There's nobody out there. Not hiding. Not too far away to detect. Not using communication methods we haven't invented yet. Just absent. The universe is empty because complex life is extraordinarily rare, and we happen to be the exception. This is called the rare Earth hypothesis, and most people don't realize how much scientific weight it carries. The idea isn't that life is impossible elsewhere. It's that the specific chain of conditions required to produce intelligent technological life is so improbable that it may have happened only once in the observable universe. Here, on this planet, around this particular star. Start with location, not just Earth's position around the Sun, but the Sun's position within the Milky Way. Our galaxy has regions that are hostile to complex life. The galactic center is dense with radiation, supernova activity, and gravitational disruption. The outer edges of the galaxy are too thin, too poor in the heavy elements that planets and living organisms require. There is a narrow band, sometimes called the galactic habitable zone, where conditions are stable enough, where element abundance is right, where the radiation environment is survivable. Our solar system sits inside that band. That alone narrows the candidates significantly. Now consider the star itself. Our Sun is a G-type main sequence star. It burns steadily. It doesn't flare violently. It doesn't flood the inner solar system with lethal radiation every few years, the way many smaller, more common stars do. Red dwarf stars make up roughly 3/4 of all stars in the galaxy. They are the most common type by far, but red dwarfs are active and unpredictable, especially when young. Planets close enough to sit in their habitable zones are close enough to get blasted regularly with radiation. A G-type star like the Sun is far less common and far more forgiving to anything trying to develop on a nearby planet over billions of years. Then there is the Moon. Earth has an unusually large moon relative to the size of the planet. Most moons in our solar system are small compared to their host worlds. Our moon is massive enough to stabilize Earth's axial tilt. Without it, Earth's axis would wobble dramatically over thousands of years, shifting between extremes that would make long-term climate stability nearly impossible. Stable seasons, stable climate zones, stable ocean circulation patterns. All of it depends to a significant degree on the moon holding our tilt steady. The moon formed from a collision between early Earth and a Mars-sized body called Theia. That collision was not guaranteed. It was one event among many that could easily have gone differently. Plate tectonics is another factor most people overlook. Earth's crust is broken into moving plates that grind against each other, pull apart, and dive beneath one another over millions of years. This process does something critical. It recycles carbon. Carbon dioxide gets drawn out of the atmosphere by weathering, gets locked into rock, gets pulled into the mantle at subduction zones, and gets released back into the atmosphere through volcanic activity. This carbon cycle acts like a thermostat, regulating global temperature over geological time. Without it, carbon accumulates, temperatures climb, and the planet becomes uninhabitable. Mars has no plate tectonics. Venus has no plate tectonics. Earth is unusual in the solar system simply for having it, and the origin of plate tectonics on Earth is still not fully understood. Earth also has a magnetic field generated by its liquid iron core. That field deflects the solar wind, a constant stream of charged particles flowing outward from the sun. Without it, the solar wind would strip away the atmosphere over millions of years, the same way it stripped Mars bare. Mars once had a magnetic field. It collapsed. The atmosphere thinned. The water evaporated into space. The surface became the frozen, irradiated desert it is today. Earth's magnetic field has held, but its existence depends on the planet having the right interior structure, the right rotation rate, the right thermal history. None of that was obvious from the start. Jupiter deserves its own mention. Jupiter is enormous. It sits in the outer solar system, and its gravity hoovers up or deflects a significant portion of the debris, comets, and large asteroids that would otherwise strike the inner planets far more frequently. Without Jupiter acting as something of a shield, Earth would be hit by major impacts far more often. Frequent large impacts sterilize planetary surfaces. They vaporize oceans. They collapse ecosystems. The dinosaur-killing impact 66 million years ago was one event. Imagine that happening dozens of times more frequently, and complex multicellular life would struggle to gain any foothold at all. And then there's the biological side of this. Even granting a planet with all the right physical conditions, life still has to emerge. Single-celled life appeared on Earth relatively quickly after the surface cooled, which suggests it may not be extraordinarily rare. But eukaryotic cells, cells with a nucleus, with complex internal machinery, took almost 2 billion years to appear. And multicellular life took another billion years after that. These transitions were not inevitable. The leap from simple bacteria to complex cells may have required an extremely unlikely merging event between two different types of microbes. It happened once in Earth's history that we can identify. Once in 4 billion years of life on this planet. Consciousness, language, technology, each of those builds on the step before. Each requires a long, unbroken chain of circumstances to hold together across hundreds of millions of years. A slightly different impact at the right time would have redirected evolution entirely. A different atmospheric composition would have selected for different organisms. Every step in the chain had to work, not just on geological timescales, but on biological ones too, through mass extinctions, ice ages, and climate swings that wiped out enormous fractions of all life on Earth multiple times. Most people find it easier to imagine the universe full of life than to sit with the possibility that it isn't. The numbers are so vast that absence feels statistically impossible. But the rare Earth hypothesis doesn't argue against large numbers. It argues that each additional requirement for complex life multiplies the improbability. One unlikely condition is survivable in the math. 10 unlikely conditions simultaneously required is not. 20 or 30 begins to produce a number so small that even the hundreds of billions of galaxies in the observable universe might not be enough to guarantee it happening twice. A 2024 paper in Scientific Reports made the case that even plate tectonics combined with persistent oceans over billions of years may be geologically unusual among rocky planets. If that single combination is rare, then everything built on top of it, all the complexity, all the biology, all the eventual intelligence, inherits that rarity. We got lucky in a way that might never happen again anywhere in the observable universe. But there's another way to look at the emptiness, and it's darker. The rare Earth idea at least offers something close to comfort. If complex life is extraordinarily rare, then the universe being quiet makes sense. There's nobody out there to hear. But an economist named Robin Hanson looked at the same empty sky in 1998 and arrived at a different conclusion. He wasn't asking why life was rare. He was asking something harder. Why, given billions of years and billions of stars, has no civilization ever left a mark on the galaxy that we can detect? His answer was the Great Filter. The core idea is straightforward. Between simple chemistry and a civilization that spans the stars, there are many steps. Life has to begin. Single cells have to become complex cells. Complex cells have to organize into multicellular organisms. Those organisms have to develop nervous systems, then brains, then intelligence, then technology, then the ability to survive long enough to reach other worlds. Each of those steps has to work, and Hanson's argument is that somewhere in that chain, there is one step so difficult that almost nothing makes it through. Not most species, not even a large fraction, almost none. That step is the Great Filter. The reason we know a filter exists is precisely because the universe is empty. That's the key insight. We're not inferring the filter from probability alone, we're inferring it from observation. If the path from chemistry to civilization were relatively smooth, the galaxy should be full of civilizations by now. Some of those civilizations would have had billions of years more than us to develop. A species just 1 million years more advanced than humanity would be capable of things we can't begin to conceptualize. They'd have had time to colonize every star system in the Milky Way many times over. We'd see unmistakable evidence of them everywhere we looked. We see none. So something is filtering. The question is where. One candidate is the origin of life itself. We still don't know how chemistry became biology. We know it happened on Earth roughly 3.8 billion years ago, possibly earlier. But the exact mechanism remains one of the hardest unsolved problems in science. Going from a mixture of organic molecules to a self-replicating system that can copy itself and pass on information is not a simple chemical reaction. It may require an extraordinarily unlikely series of molecular accidents. If the first step from chemistry to living cell is the filter, then life itself is the rarity. Simple microbial life would be nearly non-existent across the universe. We'd be truly alone, not because we're advanced, but because the first foothold was almost impossible to find. Another candidate sits deeper in the history of Earth's biology. For roughly 2 billion years after life appeared here, nothing existed except single-celled organisms without a nucleus. Then, around 1.8 billion years ago, something remarkable happened. A cell absorbed another cell and, instead of digesting it, kept it. The result was the eukaryotic cell, a far more complex structure with a nucleus and specialized internal components. Every plant, every animal, every fungus on Earth descended from that event. It may have happened only once. If that kind of merger is the filter, then simple bacterial life could be scattered throughout the galaxy, quietly metabolizing, never going anywhere. No complexity, no nervous systems, no eyes or brains or hands. Just a universe carpeted in microbes, thus had never took the next step. Then there's the jump to multicellular life. Single-celled organisms existed for billions of years before cells began cooperating in stable, differentiated structures. A liver cell and a neuron contain identical DNA but behave completely differently, and coordinating that kind of specialization across trillions of cells without the whole system falling apart required biological machinery of staggering sophistication. The Cambrian explosion, roughly 540 million years ago, saw complex animal body plans appear in the fossil record in a geologically brief window. Before that, for the vast majority of Earth's biological history, nothing with a body plan existed at all. That transition might be rarer than it looks. Beyond multicellular life, there's the development of intelligence itself. Billions of species have lived on Earth. Almost none developed anything we'd call complex cognition. Nervous systems evolved independently many times, but large brains capable of abstract reasoning, language, and cumulative culture appear to have emerged just once in the particular lineage that led to humans. It's possible that intelligence is simply not a natural endpoint of evolution. Evolution doesn't aim anywhere. It responds to local pressures. Most environments don't reward the kind of metabolically expensive brain that humans carry. Intelligence might be an accident, a quirk of one particular evolutionary path on one particular planet, rather than an inevitable destination. And then there is technology. Even granting intelligence the path from a thinking animal to a civilization capable of radio telescopes and rockets and interstellar ambitions is not guaranteed. Early humans existed for 200,000 years before the agricultural revolution. Civilization in its current technological form is less than 300 years old. Other intelligent animals on Earth, dolphins, elephants, great apes, never built anything. The conditions that led to human technological development may be unusual in ways we haven't fully identified. The statistical weight of these multiple barriers compounds dramatically when considered together. Earth produced roughly 5 to 10 billion species across its history, yet only one achieved technological civilization. That single outcome from billions of attempts suggests the filters are extraordinarily restrictive. When scientists calculate the combined probability of clearing every barrier, from chemistry to life to eukaryotes to multicellular organisms to intelligence to technology, the numbers become almost incomprehensibly small. The universe would need to be far larger than it is, with far more habitable planets producing life, for such a chain of improbable events to occur even once. This cascade of rarity means that even if multiple worlds harbor simple life, the conditions for some, anything like human civilization, may be unique or nearly so. Each of these candidates is a plausible location for the filter. Any one of them could be the wall that almost nothing crosses. And there may be more than one. The total probability of making it from organic chemistry to a galaxy-spanning civilization might be the product of dozens of improbable steps, each one multiplying the difficulty. The combined result could be a number so small that across the entire observable universe, it has happened only once. Here is where the great filter becomes genuinely important rather than just intellectually interesting. We know with reasonable confidence that we have already crossed some of these steps. Life arose on Earth. Eukaryotic cells arose. Multicellular organisms arose. Intelligence arose. Technology arose. We are here. Whatever filters exist in those stages, we made it through them. If those are where the great filter sits, then we are extraordinarily lucky survivors. And the silence around us is the silence of everyone else who didn't make it. The universe is empty because the early steps are nearly impossible, and we happen to clear them. But the filter might not be behind us. It might be ahead. If the steps from chemistry to technological civilization are not especially rare, then the galaxy should be producing civilizations regularly. And something else must be stopping them from expanding across the stars. That something would have to be almost universally fatal. A barrier that advanced civilizations encounter and do not survive. If that's where the filter is, then the emptiness of the universe is not a record of how rare we are. It's a record of how many civilizations reached our current stage, or close to it, and then stopped. The filter is real, the silence proves it, but we don't know which side of it we're standing on. There's a version of this story where we're the lucky ones. If the great filter lies somewhere in our past, then the emptiness of the universe isn't a warning. It's a measure of how improbable we really are. Every planet that formed in a habitable zone, every world with liquid water and the right chemistry, started the same race. Almost none of them finished it. We did. The filter already happened to us, and we cleared it without even knowing it was there. That changes the entire meaning of the silence. The cosmos isn't a graveyard of dead civilizations. It's more like an enormous lottery that almost no one wins, and we happen to be holding a ticket. The question is where exactly in our history the filter sits. There are several candidates, and each one represents a step so improbable that most planets with life never managed it. The first candidate is life itself. Getting from raw chemistry to a self-replicating molecule capable of passing information to the next generation is not a simple step. Chemists have been studying this problem for decades, and it remains genuinely unsolved. We know life appeared on Earth within a few 100 million years of the planet cooling enough to support it. That sounds fast. But fast doesn't mean easy. It could mean we got extraordinarily lucky very early. If the origin of life requires a specific chemical accident that almost never happens, then most planets with the right conditions simply sit there, warm and wet, with no life at all. The universe would be full of sterile oceans. But suppose life does arise commonly. The next candidate is the jump from simple bacteria to complex cells. For roughly 2 billion years, life on Earth was nothing but single-celled organisms with no nucleus. They were simple. They were successful. They showed almost no sign of evolving further. Then, about 2 billion years ago, something extraordinary happened. One cell absorbed another, and they began working together. The result was the eukaryotic cell, a far more complex structure with a defined nucleus, organelles, and the machinery necessary for all complex life that followed. Every animal, every plant, every fungus on Earth is built from cells that descended from that single event. It may have happened only once. In 2 billion years of bacterial life, it appears to have occurred exactly one time. If that transition is genuinely rare, then most biospheres are stuck at bacteria permanently. Even if a planet makes it to complex cells, there's still the transition to multicellular life, the development of sexual reproduction, the emergence of large bodies and nervous systems, and eventually the very specific kind of intelligence that builds tools and asks questions about the universe. Each of those steps is another potential filter. Each one might require conditions and probabilities that don't come together easily. The Cambrian explosion is worth pausing on. About 540 million years ago, animal life on Earth diversified with remarkable speed. Dozens of new body plans appeared in the fossil record within a relatively short geological period. Eyes, limbs, shells, complex nervous systems, all emerging in what amounts to an evolutionary blink. For billions of years before this, life was soft, simple, and slow to change. Something changed, and suddenly the planet was producing complexity at an accelerating rate. We don't fully understand why it happened when it did. If whatever triggered that explosion had never occurred, Earth might have remained a world of simple organisms indefinitely. Large brains require large bodies. Large bodies require the kind of ecological complexity the Cambrian unlocked. Then there's the issue of geology. A 2024 paper in Scientific Reports argued that Earth's specific geological history may be genuinely unusual. The combination of plate tectonics operating continuously for billions of years alongside persistent oceans covering a significant portion of the surface creates a carbon cycle that regulates temperature over geological timescales. Plate tectonics recycles carbon dioxide from the atmosphere back into the mantle and then returns it through volcanic activity. Without that cycle, carbon can accumulate to levels that make the atmosphere hostile or drop so low that the planet freezes entirely. Many rocky planets may lack active plate tectonics entirely. Others might have oceans that disappeared early or never formed in the right quantities. Earth's stability over 4 billion years required a geological system operating within narrow parameters for an extraordinarily long time. That combination may not be common. What makes this version of events almost comforting is what it implies about the universe. Life, under this interpretation, almost certainly exists elsewhere. Microbial life may be everywhere. Simple organisms clinging to the inside of rocks on cold moons, drifting in the clouds of distant planets, surviving in hot vents at the bottom of alien oceans. The universe might be full of bacteria, but bacteria don't build radio telescopes. Bacteria don't write mathematics or point instruments at the sky and wonder who else is out there. The filter between a bacterium and a technological civilization is almost incomprehensibly wide, and if any part of that gap requires a near miracle to cross, then we crossed it. Most other worlds didn't. There's something genuinely staggering about that thought. Earth is not particularly special in terms of size or composition. Our sun is an average star. Our solar system sits in an unremarkable region of an ordinary galaxy. Nothing about where we are should single us out. And yet, if the filter is behind us, we are among the rarest things in the observable universe. Not because Earth is special, but because we happen to get through a series of improbable transitions that most planets never manage. We accumulated the right accidents in the right order over a long enough time that intelligence eventually emerged and looked back at the chain of events that produced it. The filter might not be a single wall, it might be dozens of them, each one taking out most of the candidates. Every planet that makes it past the origin of life gets filtered at the eukaryote step. Every planet that produces eukaryotes gets filtered at multicellular complexity. Every planet that produces animals gets filtered somewhere before large brains. And of the small fraction that makes it through everything, only some manage the specific geological stability required to sustain a biosphere long enough for intelligence to develop. Stack those probabilities together, and the number that survives becomes very small. That would mean the hardest part is already behind us, that we are, against all odds, the ones who made it through. Now here's where it gets genuinely frightening. In the previous scenario, the filter sits behind us. The hard part is already done. Life struggled for billions of years to produce something capable of asking these questions, and we happen to be the rare result. That interpretation, uncomfortable as it is, carries something almost like relief. But there is another possibility, and it points in the exact opposite direction. What if life isn't rare at all? What if simple organisms arise on planets all across the galaxy, and multicellular complexity follows, and intelligence emerges with reasonable regularity? If that's true, then the filter isn't behind us. It's waiting. Something out there, some barrier, some catastrophe, some tendency built into the nature of technological civilizations has been stopping them before they spread across the stars. And we haven't hit it yet. This is the scenario that keeps researchers genuinely unsettled. Not because it's speculative, but because the logic is hard to escape. We know the galaxy is old. The Milky Way has been forming stars for roughly 13 billion years. Earth-like planets were possible billions of years before our own planet formed. If civilizations had been arising regularly throughout that history, and if even a small fraction of them survived long enough to develop interstellar travel, the galaxy would look completely different from how it looks today. A civilization just 1 million years more advanced than us would have had time to reach every star system in the Milky Way many times over, even at speeds far below the speed of light. The galaxy should be colonized. It should be visibly modified. There should be signs everywhere. There are none. So either intelligence is extraordinarily rare, which is the previous section's answer, or something prevents civilizations from lasting long enough to spread. The universe is essentially telling us one of those two things. And if life turns out to be common, if we ever find microbial organisms on Mars or in the oceans of Europa, the rare earth argument weakens considerably. Suddenly, the filter has to be somewhere else, somewhere closer to us, somewhere we haven't passed yet. The candidates aren't abstract, they're specific, and several of them are already active. Nuclear weapons are the most obvious starting point. We built the first functional nuclear device in 1945, less than 80 years ago. In the decades that followed, we came close to using them more than once. The Cuban Missile Crisis in 1962 brought the world within hours of a full-scale nuclear exchange. There were incidents during the Cold War where early warning systems malfunctioned and reported incoming missiles that didn't exist. In at least one documented case, a single Soviet officer named Stanislav Petrov declined to report what his system showed as an American first strike. He suspected a malfunction and decided not to escalate. He was right. His individual judgment on one particular night in 1983 may have prevented a nuclear war. That's how close it gets. That's how thin the margin is. We have had nuclear weapons for less than a century, and we nearly destroyed ourselves with them multiple times already. And nuclear warfare is just one candidate. Engineered pathogens represent a different category of risk entirely. Biology is becoming easier to manipulate. The tools required to modify dangerous organisms are becoming cheaper and more accessible every decade. What once required a government-funded laboratory can now be approximated in smaller, less controlled settings. A civilization that develops this kind of biological capability doesn't need to intend catastrophe to cause it. A single accident, one miscalculation, one rogue actor with sufficient knowledge could release something with the potential to move faster than any response system could contain. We got a limited preview of what a global pandemic looks like in a modern, interconnected world. The next version, engineered rather than natural, could be considerably worse. Artificial intelligence introduces a different problem altogether. We are building systems of increasing capability whose internal processes we don't fully understand. Large AI systems already make decisions in ways that their designers cannot easily trace or explain. The goal in AI development has largely been to make these systems more capable, more autonomous, more effective. What receives considerably less attention is the question of whether systems with those properties will remain aligned with human interests as they grow more powerful. This isn't science fiction speculation. The researchers closest to the technology are among the most vocal about these concerns. A sufficiently advanced AI system pursuing an objective that seems benign could cause civilizational damage simply by optimizing for that objective in ways its creators didn't anticipate. We are accelerating into this territory without having solved the foundational alignment problems that make it safe. Ecological collapse and climate destabilization operate on a slower timescale but are no less real as civilizational threats. A technological species requires a stable biosphere. It requires predictable agriculture, reliable water systems, functioning ecosystems that regulate temperature and atmosphere. We are actively degrading all of those systems at the same time. The planet we depend on is becoming less stable in ways that compound. Extreme weather events become more frequent. Agricultural disruption increases. Freshwater availability declines in densely populated regions. Civilizations that are already under pressure from scarcity and displacement become more prone to conflict. These pressures don't have to cause extinction directly. They just have to create enough instability to knock a civilization off the trajectory it needs to stay on. Resource exhaustion works through the same mechanism. A civilization that consumes faster than it can develop alternatives eventually runs into hard limits, and the transition period between what it has and what it needs can be catastrophically destabilizing. What makes all of this genuinely alarming in the context of the Fermi Paradox is the convergence. We aren't facing one of these risks in isolation. We are facing most of them simultaneously, and we're doing so as a single planet species with no backup. Every human being, every piece of accumulated knowledge, every institution and city and cultural achievement exists on one fragile world orbiting an ordinary star. A civilization that spread itself across multiple star systems over millions of years would be essentially indestructible. We have not done that. We have barely left our own planet. If something goes wrong here, it goes wrong everywhere we are. The timing matters in this framework. If technological civilizations routinely survived and expanded, the galaxy would show evidence of it. It doesn't. That means civilizations that reach our current stage of development must, in most cases, fail to progress beyond it. They might destroy themselves outright. They might collapse into a pre-technological state from which recovery never comes. They might survive but never achieve the stability required to expand. Whatever the mechanism, they stop. And the evidence for this comes not from a single observation but from the sheer scale of the universe's silence. The absence of advanced civilizations isn't a small data point. It represents billions of years of galactic history across hundreds of billions of star systems. That silence is telling us something. We tend to think of our current period as progress, and in many ways it is. We've doubled life expectancy, reduced extreme poverty, built global communication networks, developed medicine capable of eliminating diseases that once killed millions. These are genuine achievements. But technological progress is not the same thing as civilizational stability. The same advances that have made us more capable have also given us more powerful ways to fail. Each new capability comes with a corresponding new category of catastrophic risk. The more powerful the technology, the larger the potential consequences of misuse or mismanagement. Other civilizations, wherever they were, presumably thought of themselves as progressing too. They were presumably solving problems, building systems, developing tools. And yet, the galaxy is quiet. Not just somewhat quiet. Completely, profoundly, unambiguously quiet. That quiet is the data. And the data suggests that making it through this phase, the phase we are currently in, is not something most civilizations manage to do. The universe isn't empty because civilizations are rare. It might be empty because civilizations are fragile. And the most dangerous moment is exactly where we are right now. There's a theory that flips the entire problem on its head. Every explanation we've covered so far assumes the universe is quiet because civilizations are rare or dead or simply haven't found us yet. But Chinese science fiction author Liu Cixin proposed something fundamentally different. The universe isn't empty, it's full of civilizations. They're just hiding. And they're hiding because showing yourself is the most dangerous thing you can do. The theory is called the dark forest. The name comes from an image, a dark forest at night, full of hunters moving in silence, each one aware that others are out there, none of them willing to make a sound. Because in the dark forest, the moment you reveal your position, you become a target. The logic begins with two simple facts about the universe. First, resources are finite. Every star system has a limited supply of matter and energy. Every civilization needs those resources to survive and expand. Second, civilizations can never fully trust each other. You can't verify another civilization's intentions. You can observe their technology and their behavior, but you can never be certain what they'll want 1,000 years from now. A civilization that seems peaceful today might become expansionist tomorrow, and the distances involved mean that by the time you detect a threat, it may already be too late to respond effectively. From those two facts, a brutal logic follows. If you detect another civilization, you face a choice. You can make contact, reveal yourself, and hope they're peaceful, or you can eliminate them before they become a threat. The problem is that choosing contact means gambling your entire civilization on a stranger's goodwill, and the cost of being wrong is extinction. Under this framework, the rational move is always the same. Strike first and ask questions never. Not out of malice, but out of pure survival logic. Any civilization that thinks carefully about the situation arrives at the same conclusion: silence, concealment, and elimination of anything that isn't silent. This is a cosmic prisoner's dilemma scaled to the size of a galaxy. In game theory, a prisoner's dilemma is a situation where two parties would both benefit from cooperation, but the risk of being betrayed makes defection the rational individual choice. Here, the defection strategy is preemptive destruction. If every civilization runs this calculation, the result is a galaxy where everyone hides and everyone destroys any signal they detect. Not because they're hostile by nature, because the math leaves no other option. The universe becomes quiet, not through scarcity, but through terror. What makes this theory genuinely unsettling is how well it fits the evidence. The silence isn't evidence of emptiness, it's evidence of discipline. Every civilization that survived long enough to understand the game learned to go dark. The ones that didn't learn are gone. The universe we observe is the universe filtered through billions of years of this selection pressure. Only the hidden survive. Only the quiet endure. The silence we hear when we point our telescopes at the sky might not be the silence of a graveyard. It might be the silence of an ambush. Liu Cixin first laid this out in detail in his 2008 novel, The Dark Forest, the second book in the three-body problem trilogy. But the logic he describes isn't just fiction. It's derived from realistic assumptions about resource competition and the limits of trust between unknown parties. Evolutionary biology operates on similar principles. Organisms don't extend unlimited trust to strangers. They assess threats and act accordingly. Scale that instinct to civilizations capable of destroying planets, and the dark forest becomes less a metaphor and more a prediction. Some researchers push back on this reasoning. They argue that a sufficiently advanced civilization wouldn't need to fear resource competition. A Type 3 civilization harvesting the energy of an entire galaxy would have more than enough. They argue that intelligence might converge on cooperation rather than elimination. These are reasonable objections, but they assume that all civilizations reach that level of advancement without incident, and they assume a uniformity of values that may not exist. All it takes is one civilization that didn't develop past aggression, one that still runs on survival logic, to make the entire dark forest real for everyone else. A single predator in the woods changes the behavior of every other creature in it. The deepest implication of the dark forest isn't about other civilizations, it's about us. We discovered radio communication in the late 19th century. We began broadcasting television and radio signals into space in the early 20th century. Those signals have been expanding outward at the speed of light ever since. A sphere of human electromagnetic noise now extends roughly 100 light-years in every direction from Earth. That sphere contains a few thousand star systems. Any civilization within that radius with the right detection equipment would know we exist. They would know our location. They would know our approximate level of technology from the content of our broadcasts. They would know we are here. And we didn't stop there. In 1974, astronomers transmitted the Arecibo message directly toward a star cluster about 25,000 light-years away. It was a deliberate, targeted signal carrying information about our biology, our chemistry, our mathematics, and our location. In 2008, a transmission called A Message from Earth was sent toward a planet in the Gliese 581 system. Scientists have debated whether these deliberate transmissions were wise. Some of the most prominent figures in science, including Stephen Hawking, warned explicitly that broadcasting our existence is reckless. Hawking compared it to the indigenous peoples of the Americas advertising their presence to European explorers, a comparison that, given that history, is not comforting. Most scientists who study the Fermi Paradox don't endorse the dark forest theory outright. The assumptions it requires, that resource competition is unavoidable, that trust is impossible, that preemptive elimination is always preferred over contact, are significant ones. A universe full of civilizations all independently choosing to hide would require that every one of them, without exception, ran the same calculation and reached the same result. That's a strong assumption, but it doesn't need to be universally true to be effective. The logic only needs to apply to a significant fraction of civilizations. If even 1 in 10 advanced species becomes a predator, the others will learn caution quickly. The ones that don't learn are no longer around to teach the lesson. The observable result is the same either way. A universe of hidden, cautious civilizations and a universe of absent ones look identical from the outside. Both are silent. Both appear empty. You can't tell the difference by listening. We've been transmitting our location into the darkness for over 100 years, and under this theory, that might be the most dangerous thing humanity has ever done. Maybe the silence isn't because they're gone or hiding. There's another possibility entirely, and in some ways it's the strangest one of all. What if advanced civilizations know we're here and they've simply decided to leave us alone? This is the zoo hypothesis, first proposed by astronomer John Ball in 1973. The idea is straightforward. Intelligent civilizations exist throughout the galaxy. They're aware of Earth. They've watched us for a long time. But they've made a deliberate choice not to make contact, not to interfere, not to reveal themselves. We are, in this picture, the animals in the zoo. They are the visitors on the other side of the glass. Ball's argument was built on a simple observation. The absence of contact doesn't necessarily mean the absence of intelligence. It could mean the presence of restraint. A civilization advanced enough to cross interstellar distances, or even just to monitor radio transmissions across the galaxy, would also be advanced enough to enforce silence if it chose to. Their technology would be so far ahead of ours that hiding from us would require almost no effort on their part. We wouldn't know what to look for. We'd have no way to detect their presence unless they wanted us to. There's a reason a sufficiently wise civilization might make this choice. Earth's own history offers a grim model. When technologically advanced civilizations encountered less developed ones, the results were almost always catastrophic for the weaker party. European contact with indigenous populations in the Americas, Africa, and the Pacific didn't just bring new technology. It brought disease, displacement, cultural destruction, and in many cases, outright extinction of entire ways of life. The more powerful civilization didn't have to be malicious for the damage to occur. The imbalance alone was enough. A civilization millions of years more advanced than us would represent a gap so enormous that even well-intentioned contact might shatter everything we are. Language, culture, religion, science, the entire framework through which we understand reality, all of it could collapse on contact with something so far beyond our comprehension. A civilization that understood this might adopt a strict policy of non-interference, not because they don't care about us, but precisely because they do. They might reason that we need to develop on our own terms, reach our own conclusions, build our own understanding of the universe. Intervention, however gentle, would contaminate that process. It's the same reasoning behind a scientist observing wildlife without disturbing the habitat, or an anthropologist documenting an isolated culture without introducing outside influence. The ethical choice is to watch and wait. Star Trek fans will recognize this immediately. The Federation operates under a rule called the Prime Directive. No contact with civilizations that haven't yet developed warp travel. No interference in the natural development of pre-spacefaring societies. The reasoning within the show mirrors Ball's reasoning almost exactly. And what's interesting is that Gene Roddenberry didn't invent this idea from nowhere. He formalized something that thoughtful people were already grappling with. The zoo hypothesis and the Prime Directive emerged from the same underlying intuition about the ethics of contact between unequal civilizations. A 2024 paper in Scientific Reports focused on plate tectonics and the conditions for complex life raised the possibility that mature civilizations might converge on shared ethical frameworks as a condition of their survival. The argument goes something like this. Any civilization that reaches a high level of technological development had to solve certain problems along the way. War, resource depletion, environmental destruction, internal conflict. Solving those problems requires developing wisdom alongside power, and that wisdom might naturally lead to a shared recognition that interfering with developing worlds causes harm. Under this interpretation, non-interference isn't a rule imposed from outside. It's a conclusion that every sufficiently advanced civilization reaches independently. The ethics converge because the reasoning is universal. It's a genuinely appealing picture. The universe isn't hostile or empty. It's full of patient observers, quietly watching our civilization fumble its way toward something greater. Maybe the silence is kindness. Maybe we're being given room to grow. But the hypothesis has a problem, and it's a significant one. It requires every single advanced civilization to agree. Not most of them, not the majority, everyone. All it takes is one civilization that doesn't share the ethical consensus. One culture that values contact over restraint. One species that is simply curious enough to say hello regardless of the consequences. One rogue actor, one outlier, one civilization that looked at the situation and decided the rules didn't apply to them. Consider how difficult universal agreement is even on a single planet. Humanity has never managed to coordinate every nation, every culture, every faction toward any shared goal. Not even goals where the stakes were obvious and the benefits clear. Now scale that up to hundreds of civilizations spread across thousands of light years, each with its own evolutionary history, its own values, its own relationship to ethics and restraint. The probability that every single one of them independently arrived at the same conclusion and held to it without exception across millions of years starts to look vanishingly small. The coordination problem gets worse the more civilizations you add. If there are 10 advanced species in the galaxy, maybe you can imagine them all maintaining the quarantine. If there are 1,000 or 10,000, the odds of perfect compliance become essentially impossible to defend. Civilizations change over time, their values shift, their leadership changes, factions emerge. The civilization that agreed to the quarantine 1,000,000 years ago might not exist in the same form today. What enforces the agreement across that span of time? Some versions of the zoo hypothesis suggest a dominant civilization enforces the silence, a kind of galactic authority that maintains the quarantine through superior technology. But that just moves the problem. Why would every other civilization accept that authority? Why wouldn't some resist? And how does an enforcing civilization maintain control across the entire observable galaxy without eventually revealing itself to us through the act of enforcement? But the math makes it harder and harder to believe the quarantine holds. The more civilizations you assume exist, the more impossible it becomes that every single one stayed quiet. Then there's the answer that makes every other answer seem comforting by comparison. Every explanation we've covered so far assumes the universe is real. The stars are real. The distances are real. The silence is a genuine feature of a genuine cosmos. But there's a hypothesis that pulls the floor out from under all of that. It starts with a question. If a civilization becomes advanced enough to run detailed computational simulations of entire universes, and if those simulations can contain conscious observers who believe they're real, then how many simulated universes would exist compared to one real one? The answer is probably many more simulated ones. And if that's true, the odds that any given observer exists in the base reality rather than a simulation are vanishingly small. This is the core of the simulation hypothesis. It's not science fiction. Philosophers and physicists take it seriously. Nick Bostrom formalized the argument in 2003, and it hasn't been dismissed since. Applied to the Fermi Paradox, the logic is clean. If our universe is a computational simulation created by some advanced intelligence outside it, then the emptiness isn't a mystery at all. It's a design choice. The programmers simply didn't include other civilizations. The universe was built with one inhabited world, and everything else is set dressing. Stars by the hundreds of billions, galaxies by the hundreds of billions more. Vast stretches of space and time with no one in them, all of it rendered to create a convincing backdrop for the one experiment the simulators cared about. The silence isn't evidence of a filter. It isn't evidence that life is rare. It's evidence that whoever built this place didn't put anyone else in it. There's a variation of this idea that's arguably stranger. It's called the planetarium hypothesis. Under this version, we're not necessarily inside a full simulation of the universe. Instead, something has constructed a kind of false sky around us, a cosmic stage set. Advanced technology, far beyond anything we can currently imagine, could in principle project an image of an empty universe onto the observable horizon. Telescopes would detect fabricated signals. Radio scans would return manufactured silence. Every photon arriving at Earth from distant galaxies could be part of a constructed display. The real universe outside this projection might be full of civilizations, but we would have no way of seeing them because what we're seeing isn't real. The planetarium hypothesis was proposed in part to explain why the universe looks so uniform, so precisely calibrated, so apparently fine. Tuned for our existence, someone built it that way, and they built it to look empty. Both versions share a deeply unsettling implication. Every piece of evidence we've ever gathered about the cosmos could be unreliable. The Hubble Space Telescope's images of distant galaxies, constructed. The radio silence that SETI has documented for decades, programmed. The cosmic microwave background radiation, the oldest light in the universe, rendered. Our entire scientific understanding of the cosmos rests on the assumption that observations reflect reality. If the simulation is good enough, that assumption cannot be verified. We can't peer outside it. We can't test the edges. The instruments we would use to check are themselves part of the system we're trying to check. Most people find this uncomfortable enough to dismiss quickly. But the dismissal is harder than it looks. There's no physical test you can run that would distinguish a perfect simulation from base reality. There's no observation you could make that would settle it. Scientists generally prefer hypotheses that can at least in principle be falsified, and this one resists that almost entirely. A few physicists have proposed that a simulation running on finite computational resources might leave small signatures, subtle rounding errors in the laws of physics at the smallest scales. Some have pointed to the pixelated nature of quantum mechanics, the fact that energy and space-time appear to come in discrete chunks, as potentially consistent with underlying computational structure. These arguments remain speculative. They don't prove anything, but they haven't been fully closed off either. What makes this particular answer so different from all the others is what it implies about science itself. The great filter, the rare Earth hypothesis, the dark forest. All of those are unsettling, but they're unsettling within a framework where reality is real and observations mean what they appear to mean. The simulation hypothesis strips that away. If it's true, then every paper ever published in astrophysics is a study of carefully arranged code. Every discovery about stellar evolution, galactic structure, the age of the universe, documentation of a fiction. The cosmos as we understand it might be less than a century old in the time of whoever created it, assembled from stored data the moment we aimed instruments at it. The universe would only exist in detail where it's been observed. The rest might not be rendered yet. That last part is worth sitting with. If computational resources are finite, even for an advanced civilization, a simulated universe might only generate full detail on demand. The regions of space we've never observed might not exist in any meaningful sense. They would be filled in when we look. The emptiness we find there might not be a feature of the universe. It might be a feature of the rendering engine. Other civilizations might exist in the code but simply haven't been loaded into the parts of the simulation we can reach. We would search and find nothing, not because they're absent, but because the simulation hasn't generated them yet in any observable form. You can't disprove it, which, if you think about it, is either deeply reassuring or the most unsettling thing imaginable. There's another possibility that doesn't require civilizations to be rare or dead. It doesn't require a great filter or a dark forest or a cosmic quarantine. It just requires that civilizations are hard to detect and only for a very short window. That window might be so short that finding another civilization during it would be almost miraculous. Think about what our own civilization looks like from the outside. We invented radio broadcasting around 1900. From that point forward, we began leaking electromagnetic radiation into space at an accelerating rate. Radio signals, television transmissions, military radar, satellite communications, all of it radiating outward from Earth at the speed of light. For about a century, we were loud. An alien civilization pointing a sufficiently powerful telescope at our solar system during the 20th century would have had something to work with. But that window is already closing. We are moving toward fiber optic cables that carry signals underground and undersea, directed communication systems, encrypted digital transmissions that look like noise to any outside observer. The broad, in officie, NT radio broadcasts that made us detectable are already fading. If this trend continues for another 50 years, we may become effectively invisible to any civilization using the same methods SETI uses to scan the sky today. That's us, a civilization that happened to broadcast loudly for roughly 1 century out of a history that stretches back hundreds of thousands of years. 1 century. If any civilization within 1,000 light years pointed the right instruments at Earth for that specific century, they had a chance. Before that window, nothing. After that window, nothing detectable. If their search happened to miss those 100 years, they concluded no one was home. Now apply that logic to every civilization in the galaxy. Each one invents radio at some point. Each one broadcasts for some period before developing more advanced methods. Each one eventually transitions away from detectable emissions. The question is how long that transition takes. If civilizations typically spend only 50 years in the radio loud phase before moving to tighter, more directed communication systems, the chances of 2 civilizations being simultaneously detectable to each other across thousands of light years becomes extraordinarily small. It's not that no one is out there, it's that everyone moves through the detectable window so quickly that they almost never overlap. And the technology doesn't stop at fiber cables and directed beams. Civilizations might develop quantum communication methods that are inherently impossible to intercept or detect from the outside. They might transmit information in ways we haven't theorized yet, using physics we don't fully understand. A civilization 1,000,000 years more advanced than us could be communicating constantly, actively, densely across the entire galaxy. We would have no idea. We're listening for the technological equivalent of smoke signals, while they may have moved on to something we don't even have a name for. Most people don't realize how anthropocentric our search actually is. SETI listens at frequencies that make sense to human engineers using human assumptions about what a transmitting civilization would do. Those assumptions are based on roughly 120 years of radio technology. That's an extraordinarily narrow foundation for making predictions about a universe 14 billion years old. But there's another layer to this problem, and it has nothing to do with communication technology. It has to do with time and distance in a way that makes the problem almost geometrically unsolvable. When we observe a civilization 1,000 light years away, we're seeing it as it was 1,000 years ago. The light carrying that information left their world during the 11th century by our reckoning. Whatever they look like now, whatever they're doing today, won't reach us for another 1,000 years. Now imagine trying to have a conversation across that gap. You send a signal. 1,000 years pass before it arrives. They respond. Another 1,000 years pass before you receive the reply. A single exchange takes 2,000 years. The civilization that sent the original signal might not exist by the time the reply comes back. The civilization that responds might not exist by the time we receive their answer. The round-trip communication time alone exceeds the lifespan of many civilizations. This means the galaxy could be full of civilizations that are genuinely trying to make contact, sending signals in all directions, building large transmitters, searching the sky carefully, still never meaningfully connecting with anyone. They're not silent. They're separated by time as much as by distance. Their signals are crossing the galaxy right now, aimed at stars that hosted civilizations 500 years ago. Those civilizations are gone. The signals keep traveling outward into empty space, past stars that haven't yet produced life, toward destinations that will never receive them. We might be transmitting into exactly this situation. Our own radio bubble has expanded about 120 light years from Earth. That sounds significant until you realize the Milky Way is roughly 100,000 light years across. Our signal has reached perhaps a few thousand star systems out of the several hundred billion in the galaxy. And the civilizations within that small bubble either weren't there, weren't listening, weren't at the right technological stage to detect us, or have already moved past the window where our signals would mean anything to them. The detectability window problem doesn't offer comfort exactly, but it does offer an alternative to the darker explanations. The universe might be inhabited and active and full of intelligence that we simply cannot perceive. Not because they're hiding, not because they're dead, not because we're alone. Just because the physics of communication across stellar distances is brutal. Because technology advances faster than signals travel. By the time we become sophisticated enough to recognize what they're doing, they've already moved somewhere we can't follow. Here's the thing about the silence that most people don't sit with long enough. It's not just a puzzle about distant stars and alien civilizations. It's potentially a data point about us, about what happens to species that reach exactly the stage we're at right now. That reframe changes everything about how you read the emptiness. Think about what we've established. The universe is enormous. The conditions for life appear to be widespread. The math says civilizations should exist in numbers we can barely count. And yet, silence. The standard interpretation is that this tells us something about how rare life must be, or how short detection windows are, or how well advanced civilizations hide. All of those explanations focus outward, but there's another way to read the same data. The silence might not be telling us about them at all. It might be telling us about ourselves, specifically about where we are in our own story. If the great filter lies ahead, then civilizations don't fail randomly. They fail at a particular stage. They reach some threshold of technological capability, and then they stop. Not because the universe destroyed them from outside, but because something about reaching that level of power made their continued survival extremely unlikely. The filter isn't a natural disaster waiting in the dark. It may be a consequence of the very tools that civilizations build on the way up. And when you look at what we've built in the last 100 years, the pattern becomes uncomfortable to ignore. We invented nuclear weapons in 1945. Within a decade, multiple nations had them. We came within hours of using them during the Cuban Missile Crisis in 1962. We have had dozens of close calls since, some involving technical malfunctions, misread radar signals, individual officers choosing not to follow protocol. Most people don't realize how many times catastrophe was avoided not through policy or system design, but through the judgment of a single person under extreme pressure. Right now, roughly 9 nations hold an estimated 13,000 warheads. That number has declined from its Cold War peak, but the weapons still exist. The capacity to end our civilization remains fully intact. Climate change is a slower version of the same logic. We built an industrial civilization that runs on burning carbon. That process is altering the atmospheric chemistry of our planet in ways that will take thousands of years to fully stabilize. We've known about this problem for decades. The scientific consensus has been clear for a long time. And yet the systems we built to run our economies, our supply chains, our energy infrastructure, are deeply resistant to rapid change. The difficulty isn't that we don't understand what's happening. The difficulty is that the civilization we constructed to get here is precisely the one that's causing the problem. Changing it requires a level of coordination that no species has ever had to manage before. Engineered biology adds another layer. We can now synthesize pathogens in laboratories. The barrier to creating dangerous biological agents is dropping as the underlying technology becomes cheaper and more accessible. A pandemic caused by a naturally occurring virus cost millions of lives and came close to overwhelming global health systems. An engineered pathogen designed to spread efficiently and evade immune responses could be far worse. We don't need a nation-state to threaten this anymore. The capabilities are approaching the point where a small group with the right knowledge and access could cause catastrophic harm. And then there's artificial intelligence. We are building systems that can process information and recognize patterns at scales beyond anything human minds can match. Most experts believe that within decades, those systems will exceed human-level performance across essentially every cognitive domain. The honest answer is that nobody is certain what happens after that. The development is accelerating faster than our institutional legal and ethical frameworks can keep up. The engineers building these systems are largely aware of the risks. The competitive pressures pushing the development forward are enormous. It's very difficult to slow down when every participant knows that slowing down unilaterally means falling behind. This is what a great filter looks like from the inside, not a single catastrophe arriving from outside. A cluster of simultaneous pressures, all arising from the same source, the rapid expansion of technological capability outpacing the development of the wisdom needed to manage it. Every one of these risks we've described is a product of human ingenuity. Nuclear weapons required physics, climate change required industrialization, engineered pathogens require biology, artificial intelligence requires computing. These aren't failures of intelligence, they're direct consequences of it. That's what makes the filter so plausible as an explanation for cosmic silence. Consider what SETI silence implies if this picture is right. Across the history of the galaxy, civilizations may have reached this same threshold many times. They invented the equivalent of nuclear power. They altered their planet's chemistry. They developed increasingly capable autonomous systems. And at some point in that sequence, they didn't make it through. Not necessarily through dramatic, sudden collapse. Perhaps through gradual degradation, resource exhaustion, or a single catastrophic miscalculation at a moment of peak vulnerability. The signal stopped. The structures decayed. Billions of years later, there's no trace left to detect. We are not looking at an empty universe. We may be looking at a universe that has processed this problem many times before. The most important shift in thinking that the Fermi Paradox demands isn't scientific, it's civilizational. When we ask where all the other civilizations are, we're implicitly asking what happened to them. And if the filter is ahead, the answer to that question is also the answer to a different question. What happens to us? The silence in the cosmos is not neutral data. It might be the most heavily weighted statistical observation humanity has ever made. Every direction we point a telescope, every frequency we scan, every survey that comes back empty, all of it is consistent with a universe where technological civilizations don't survive the transition we are currently in the middle of. We are a single-planet species. All of our infrastructure, all of our knowledge, every person alive, every institution we've built, everything that makes us what we are, exists on one world. One significant asteroid impact, one engineered pandemic, one miscalculation by a person with access to the wrong systems, and the experiment ends. There's no backup. There's no second copy of humanity waiting somewhere else while we work through our problems. We are operating without a safety net at the precise moment when the risks are highest. None of this is reason for despair. It's reason for clarity. The silence tells us something we need to hear. Every civilization that reached our point may have faced the same crossroads. Some fraction presumably made it through, or the great filter wouldn't exist as a filter, but as an absolute wall, and we wouldn't be here to observe anything at all. Making it through requires treating this period as what it actually is, the most consequential transition in the history of our species, where the decisions made in the next few generations will determine whether our civilization adds to the silence or eventually becomes one of the rare transmissions that breaks it. The empty sky isn't just a mystery about them. It might be the most urgent message we've ever received about ourselves. In August 1977, something happened that astronomers still can't fully explain. The Big Ear radio telescope was operated by Ohio State University. It was a fixed structure, unable to rotate to track objects across the sky. Instead, it relied on Earth's rotation to sweep different regions of space through its field of view. On August 15th, the telescope was scanning a region near the constellation Sagittarius as part of an ongoing search for extraterrestrial signals. A volunteer astronomer named Jerry Amon was reviewing the printed computer data a few days later. The telescope logged its data as columns of numbers and letters, each character representing signal intensity at a given frequency. Most of the printout looked ordinary. Then Amon reached one sequence that did not. The characters read 6EQUJ5. He circled them in red pen and wrote a single word in the margin. Wow. That sequence represented a signal of extraordinary intensity. The characters used to log signal strength ran from 0 to 9 and then continued through the alphabet, with each letter representing higher intensity. The letter U in that sequence corresponded to an intensity roughly 30 times above the background noise of space. Nothing in the surrounding data came close to that level. The signal lasted exactly 72 seconds, which was the precise duration Any fixed-point source in space would remain in the telescope's beam given Earth's rotation. That detail is important. It matched the expected behavior of a signal coming from a fixed point far out in space, not from something local, not from a satellite, not from ground-based interference. The frequency was equally significant. The signal appeared near 1,420 megahertz. That frequency corresponds to the emission of neutral hydrogen, the most abundant element in the universe. For decades, astronomers involved in the search for extraterrestrial intelligence had argued that 1,420 megahertz was the most logical frequency for any civilization to broadcast on, precisely because any technologically advanced species would know that hydrogen radiates at that frequency. It was considered a kind of universal marker. A signal at that frequency from a fixed point in deep space with that intensity profile matched almost everything scientists had theorized an intentional extraterrestrial transmission would look like. Researchers searched for a repeat signal immediately. Follow-up observations began within weeks. Over the following years and decades, the Big Ear telescope returned to that region of the sky more than 50 times. Other radio telescopes around the world also scanned the same coordinates. Nothing matching the original signal has ever been detected again. The signal has not repeated. It left no trace. Explanations have been proposed over the years. One early candidate was a reflection of radio frequency interference off a piece of space debris. That doesn't fit well. The frequency was too close to the hydrogen line for typical terrestrial interference, and the intensity pattern matched a natural beam sweep too precisely. Satellites were considered, but no known satellite was in the correct position. The signal also originated from a location where two of the Big Ear's feed horns should have detected it in sequence, roughly 5 minutes apart. Only one horn picked it up. That inconsistency has never been cleanly resolved. In 2017, an astronomer named Antonio Paris proposed that a pair of comets, 266P/Christensen and P/2008Y2, were in the vicinity of the signal's origin at the time, and that hydrogen clouds surrounding these comets could have produced the emission. The proposal drew significant attention. Other researchers pushed back. The comets in question were not well characterized in 1977, and critics argued that hydrogen emission from a cometary coma at that frequency would not produce a signal with the observed narrowband profile and intensity. The debate has not been settled, but most researchers who have examined the Paris hypothesis closely consider it insufficient to fully account for what Amen recorded. What remains is a signal that has no confirmed natural explanation, no confirmed artificial explanation, and no confirmation at all of any kind. It sits in the scientific record as an anomaly, a narrowband signal at the hydrogen line coming from the direction of Sagittarius, observed for exactly the duration expected from a fixed celestial source, with intensity far above background noise. It appeared once in 45 years of searching. It has not come back. The honest assessment from the scientific community is not that this was definitely an alien transmission. It is that no one knows what it was. The signal cannot be attributed to any known natural phenomenon with full confidence, and it cannot be confirmed as artificial. It exists in a category of unexplained observations that science holds open without resolution. That is an uncomfortable place for a result to sit. Most anomalies eventually get explained, equipment malfunctions get identified, interference sources get traced. This one has resisted every conventional explanation for nearly 5 decades. Most people who learn about SETI for the first time expect the big moment to look dramatic, a clear repeating pattern, a mathematical sequence, something unmistakable. What actually sits in the record is a column of letters on a thermal printout from 1977, circled by hand with a ballpoint pen, never followed by anything. One anomaly, one circled printout. One unexplained 72 seconds. And then nothing. Maybe the real picture isn't a universe that never had civilizations. Think about what a civilization actually looks like from the outside. For most of its existence, it produces nothing detectable. Early humans spent hundreds of thousands of years on this planet without emitting a single signal that would register on a distant telescope. It was only in the last century that we began broadcasting radio waves into space. 100 years out of 200,000. That's a fraction so small it's almost meaningless. And if our civilization ended tomorrow? That brief window of radio silence, the electromagnetic bubble expanding outward from Earth, would keep traveling through the galaxy long after everyone here was gone. That bubble currently extends about 100 light years in every direction. It sounds large, but the Milky Way is roughly 100,000 light years across. Our signal has reached perhaps 1/10,000th of our own galaxy. A civilization 1,000 light years away hasn't heard us yet. A civilization 10,000 light years away won't hear us for another 9,000 years. The distances are so vast that signals travel like letters sent to addresses that may no longer exist. Now consider the other direction. Imagine a civilization on a planet 4,000 light years away. They developed radio technology around the same time we did. They broadcast for 200 years, then collapsed. War, ecological failure, something we don't have a name for yet. Their signal is still traveling. It's expanding outward at the speed of light in every direction, a hollow sphere of electromagnetic noise growing larger every second, carrying the last evidence that those minds ever existed. We might receive that signal in 3,800 years. By then, they'll have been extinct for almost 4 millennia. If we tried to respond, our reply would arrive at a silent, empty world. This is the timing problem, and most people don't realize how completely it transforms our picture of the galaxy. Two civilizations don't need to be separated by enormous distances to miss each other entirely. They just need to be separated by time. Civilization A rises, broadcasts, and collapses. Civilization B rises thousands of years later in a completely different region of space. Their signal spheres never intersect. They never overlap. Two minds that could have had entire conversations instead pass through history like ships that took completely different routes across the same ocean and never saw each other's lights. Scale this up. The Milky Way is 13.6 billion years old. If technological civilizations have been arising throughout that history, even rarely, even just a few per billion years, then hundreds of them could have come and gone before our solar system even formed. Their signals have long since traveled past us, unrecognized, lost in the background noise of the cosmos. The ruins of their worlds are billions of years old. Whatever they built, whatever they transmitted, whatever they were. Time has had far longer to erase it than it took for it to exist. We tend to think of our search for extraterrestrial intelligence as a search happening right now in the present. But when we look at the sky, we are never seeing the present. We see the past. The star 400 light years away appears to us as it was 400 years ago. A galaxy a billion light years away is shown to us as it was a billion years before the present. Any civilization we detect will always be a historical civilization, not a living one. We are essentially archaeologists, reading light that left its source before we were born, before our planet formed, sometimes before our sun ignited. The universe is 13.8 billion years old. Complex life on Earth took about 4 billion years to reach us. That means there's been time, in principle, for the entire arc of our civilization to repeat itself hundreds of times over in the earlier history of the galaxy. Civilizations that peaked and ended a billion years ago had no successors close enough or advanced enough to notice them. They rose, they burned, they fell. The universe kept going without recording any of it in a way we can access. There's a specific version of this that's worth sitting with. Every signal a civilization ever sends continues outward forever. It doesn't stop when the civilization dies. It doesn't fade on any human timescale. It just keeps expanding, growing thinner as it spreads, but still technically present in the electromagnetic record of the universe. The galaxy could be threaded through with thousands of these dead signals, ancient broadcasts from civilizations that solved problems we haven't encountered yet, transmitted music or science or something we have no category for, then stopped without warning. If we had instruments sensitive enough, if we knew exactly where to look and what frequency to tune to, we might be able to hear them. The problem is we don't know which direction, which frequency, or which moment in history to target. We'd need to identify a ghost before we could look for it. We're searching for signals from civilizations we have no description of, using technology calibrated to our own assumptions about what an intelligent transmission should look like. This isn't a failure of science. It's a consequence of the scale of time involved. The universe does not preserve civilizations. It does not mark their passing. Stars keep burning long after the planets around them go quiet. There's no monument at the edge of the galaxy listing who was here and when. We might be surrounded by ghosts, the expanding light of civilizations that burned bright, broadcast their existence into the cosmos, then went dark before anyone close enough to matter could hear them. There's a problem with everything we've covered so far, and it runs deep. Every explanation we've considered, the Great Filter, the Dark Forest, civilizations rising and collapsing in the dark, all of them assume we would recognize an alien civilization if it were there. That assumption might be wrong. It might be the most important mistake we're making. We search for radio signals. The reason is straightforward. Radio is how we communicate. We built radio technology roughly a century ago and started broadcasting almost immediately. So we point enormous dishes at the sky and listen across millions of frequencies, waiting for something that sounds like us. But radio is a product of where we are in our development. It's a technology we invented, used, and may eventually abandon. An alien civilization doesn't have to follow the same path. They might have moved past radio in their equivalent of the 19th century. They might have never used it at all. Think about what we're actually doing. We're scanning the cosmos for signals that match our own communication methods. We're looking for the technological equivalent of smoke signals from a civilization that may have long since developed something we have no framework for detecting. It's not that the search is wrong. It's that the search is narrow in ways we don't always acknowledge. The same problem applies to how we look for physical evidence. Dyson spheres are a common concept in the search for advanced civilizations. The idea is that a sufficiently advanced species would build a structure around its star to capture all of its energy output. We look for stars with unusual infrared signatures because a Dyson sphere would radiate heat differently. It's an elegant idea, but it assumes that advanced civilizations want to capture all of their star's energy. It assumes they need that much power. It assumes they expand outward, build larger, consume more. That's how we think about progress. Growth, expansion, increasing energy use. That's a human framework. It might not apply to a mind that evolved on a completely different world under completely different pressures. There's another possibility that almost never gets enough attention. Some researchers have suggested that truly advanced civilizations might deliberately minimize their cosmic footprint, not because they're hiding in fear, but because they've concluded that restraint is the correct approach. A civilization that has solved its existential problems might look inward rather than outward. They might run their entire civilization on quantum processors that emit almost no radiation detectable at interstellar distances. They might have uploaded their consciousness to digital substrates so efficient that their energy signature is essentially invisible. From the outside, a civilization like that would look like an empty solar system. Our definition of intelligence itself is the problem. Intelligence, as we understand it, is the product of roughly 200,000 years of human evolution. We build, we expand, we transmit, we leave marks. We assume that any intelligence worth finding would do the same. But consciousness could have evolved in forms that don't resemble ours in any meaningful way. A distributed intelligence spread across a gas giant's atmosphere. A collective organism that experiences time on geological scales and has no concept of urgency or communication as we define it. Something that exists entirely within a computational substrate with no physical presence at all. None of these would show up in any search we're currently running. We are at our core looking for ourselves. We're looking for radio because we use radio. We're looking for megastructures because building large things is how we demonstrate capability. We're looking for planets like Earth because that's where we developed. Every search strategy we've designed carries the fingerprints of a specific kind of mind on a specific kind of world at a specific point in its technological history. That's not a criticism, it's the only place we could start. But it means the absence of evidence in our searches is much weaker proof of absence than it's sometimes treated. There's a useful comparison here. Imagine trying to find evidence of human civilization on Earth using only a metal detector. You'd find some things, old coins, buried tools, certain structures. But you'd miss most of what makes us what we are. You'd miss our literature, our mathematics, our culture, our digital infrastructure, almost everything that defines us. A sufficiently limited search tool produces silence even in the middle of a crowded city. Our current searches might be the cosmic equivalent of that metal detector. The absence of evidence in this context might simply be the absence of effort in the right directions. We've searched a small fraction of the sky at a narrow range of frequencies using detection methods built around our own capabilities and assumptions. The universe is not obligated to present itself in forms we're prepared to recognize. Life that arose on a world with different physics of chemistry, different evolutionary pressures, different timescales, might have produced minds so unlike ours that no signal they send would register as intentional, no structure they build would register as artificial, no pattern they produce would look like pattern at all to us. That's a genuinely difficult problem. It's not one we can solve by building a bigger telescope or listening across more frequencies. It requires rethinking what we're even looking for at a level most searches haven't reached yet. We might be surrounded by a universe full of minds we don't recognize because they don't think anything like us. Let's say the filter is real and it lies ahead of us. That means civilizations like ours reach a certain threshold of technological capability and then disappear. Not some of them, nearly all of them. The galaxy keeps producing intelligent life, and the galaxy keeps losing it over and over across billions of years of history we can't read. The Milky Way is 13.6 billion years old. That's a number most people don't really sit with. Our civilization has existed in a recognizable form for perhaps 10,000 years. Written language, agriculture, cities, all of it fits inside a window of roughly 10,000 years. Set that window against 13.6 billion, and the disproportion becomes almost impossible to express. If intelligent civilizations arose and collapsed throughout that entire span, each one lasting 10,000 years, the galaxy could have hosted hundreds of millions of them already. Every single one gone before we arrived. Every single one leaving nothing we can detect. That's not an exaggeration. It's a straightforward calculation. And when you run the numbers, the galaxy starts to look less like an empty place and more like a graveyard. The problem is what time does to evidence. A civilization that collapsed 1 billion years ago left structures, signals, chemistry, traces of its existence. But 1 billion years of stellar radiation degrades most materials beyond recognition. Stars in the vicinity expand, heat, and sterilize entire planetary systems. Supernovae scatter the atoms of whole worlds across light years of space. The geological record of a planet gets overwritten every few 100 million years. By the time we point a telescope at a star 1 billion light years away, we're seeing light that left before complex life existed on Earth. Any ruins that might have been there are long since undetectable, even in principle. We look for signs of past civilizations and find nothing. But that absence tells us almost nothing about whether those civilizations existed. It tells us only that they're old enough to be invisible. Consider what Earth itself might look like in 1 billion years if something happened to us today. Our cities would be gone. Our satellites would have decayed into the atmosphere or drifted off course. Our radio signals, already spreading outward at the speed of light for just over a century, would be so diffuse by then that nothing in the cosmos could distinguish them from background noise. The geological record might preserve chemical traces of industrial activity, a thin layer of unusual isotopes in the rock, a slight disruption in the atmospheric record preserved in ancient ice that no longer exists. That's it. That's everything a billion-year-old technological civilization leaves behind. A smear in the stratigraphy if the planet survives intact, which most planets don't. So what would a galaxy full of dead civilizations actually look like from the outside? It would look exactly like what we observe. Silent, apparently empty. Stars forming and burning and dying in complete indifference to the brief, complex things that occasionally arose on the planets around them. The universe doesn't keep records. There's no monument to the civilizations that came and went. No memorial to the species that looked up at the same stars we look at now, built their own instruments, asked their own versions of Fermi's question, and then stopped asking. The cosmos has no mechanism for honoring what was. It just continues. New stars form from the remnants of old ones. New planets coalesce from the dust of exploded systems. New chemistry arranges itself into replicating molecules in warm tidal pools on unremarkable rocky worlds. The process that produced us has almost certainly run many times before, and if the filter is ahead of us, the process that erased those earlier civilizations has run just as many times. This is what makes the cosmic graveyard idea genuinely difficult to dismiss. It doesn't require anything exotic. It doesn't require a mysterious force or a single catastrophic event. It only requires that civilizations are fragile at exactly the stage we're in now, and that time erases the evidence. Both of those things seem entirely plausible. There's something specific worth noting about the timing. The first generation of sun-like stars capable of hosting rocky planets in stable orbits formed roughly 9 to 10 billion years ago. That means civilizations could have been arising and collapsing for billions of years before our solar system even existed. We are not early to this galaxy. We are, in cosmic terms, quite late. The raw material for technological civilizations has been sitting in the Milky Way for an enormous fraction of its entire history. If the process runs at all, it has run many times before us, and yet here we are, looking out at an apparently pristine galaxy with no obvious signs of prior occupation, no megastructures left behind, no persistent energy signatures, no ancient beacons still broadcasting from civilizations that never came home. Either the process has never run before, which seems improbable given the age and scale of the galaxy, or the process runs and then disappears completely, leaving nothing durable enough to survive the timescales involved. We tend to think of ourselves as the first civilization to face these questions. That feeling is almost certainly wrong. It's a product of the same bias that makes every generation think it's living through the most important moment in history. The evidence doesn't tell us we're first. It tells us that everything before us is gone. The universe has probably had thousands of civilizations, each one convinced it was special, each one gone before the next one could find it. Sit with this for a moment, because it matters more than it might seem at first. Everything we've covered, the empty sky, the dead signals, the civilizations that may have risen and collapsed before we existed, points back at us. It points at this planet, this species, this particular moment in the 13.8 billion year history of the universe. And the weight of that is something most people never fully feel. Let's start with the possibility that we are rare. Not just uncommon, genuinely cosmically rare. The kind of rare where the observable universe, with its 200 billion galaxies and its sextillions of stars, may contain only one civilization capable of asking where everyone else is. If that's true, then what we've built here is not ordinary. Every observatory we've constructed, every equation we've written, every time we've pointed a telescope at a galaxy a billion light years away and worked out what it's made of, that may be the only place in the universe where anything like that is happening. There may be no other mind in the observable cosmos watching the same stars we watch. That's not a comfortable thought. It's an enormous one. The universe is approximately 93 billion light-years across in the region we can observe. It contains structures so vast they take light hundreds of millions of years to cross. And if we are truly alone, then all of that, every supernova, every colliding galaxy, every nebula quietly assembling itself into new stars, goes unwitnessed except by us. We are the universe's only audience. That responsibility is almost too large to hold in your head. But there's another version of this. If the filter is not behind us, if intelligent life arises regularly and something stops it, then our situation looks very different. In that version, we're not rare at all. We're just early in the dangerous part. We are one in a long series of civilizations that reached exactly this point. The point where technology is powerful enough to be existential, where a single bad decision or a single runaway process could end the experiment. Every civilization that made it this far and continued down the same path may have failed. Not because they were stupid, not because they were malicious, because the transition is simply that difficult. Think about how long it took to build a technological civilization. Anatomically, modern humans have existed for roughly 300,000 years. Agriculture appeared around 10,000 years ago. The Industrial Revolution was about 250 years ago. Nuclear weapons came 80 years after that. Artificial intelligence capable of matching human performance in specific domains arrived within the last decade. The acceleration is real. Each step comes faster than the last, and each step also brings new failure modes that didn't exist before. A civilization that invents nuclear weapons has roughly a century based on our own experience before it builds something even harder to contain. Most of that 300,000-year human history was spent nowhere near this threshold. We could have gone extinct countless times and it would have changed nothing in the broader universe. But now we're here. Now the decisions made in the next century may determine whether this civilization continues at all. That window, the span between inventing the technology that could destroy you and developing the wisdom not to use it, may be the great filter. And we are inside that window right now. The universe is about 13.8 billion years old. Earth formed 4.5 billion years ago. Complex multicellular life appeared roughly 600 million years ago. Technological civilization has existed for a few thousand years. Even if you're generous, we represent an almost immeasurably small fraction of cosmic time. Civilizations that arose a billion years before us, if they existed, would have had a billion years longer to solve these problems. Some of them may have succeeded. Most of them, if the silence means what it seems to mean, did not. That's the context we're operating in. Not just the history of humanity. The history of intelligence in the universe, however long and however crowded or empty that history really was. We are somewhere in that chain, and the position matters. There's something worth noting that gets lost in the fear of all this. The fact that we can reason about our own place in cosmic history at all is not trivial. We built instruments that detect light that left its source before the Earth existed. We worked out the age of the universe from the motion of distant galaxies. We reconstructed the history of life on this planet from the chemical signatures left in ancient rock. None of that had to be possible. The universe didn't owe us the laws of physics that make scientific inquiry work. It didn't owe us brains complex enough to use them. Whatever combination of circumstances produced this species on this planet at this particular moment, it produced something that can look back across 13.8 billion years and begin to understand what it's seeing. Whether we are alone or one of many, that is worth something. It doesn't make us safe. It doesn't guarantee we survive the next few centuries. But it means that the universe, at least in this small corner of it, arrived at a mind. Something that wonders. Something that builds telescopes and points them at empty space and waits for an answer that hasn't come. What we do with that is the question. If the filter is ahead of us, we are living through the most consequential period in the history of intelligence in the universe. Not the most dramatic. We've had extinctions, supernova, collisions of galaxies. But the most consequential in the sense that the outcome actually hangs on choices being made right now, by people alive right now, on a single planet orbiting an average star in an unremarkable spiral arm of one galaxy among hundreds of billions. The civilizations that didn't make it, if they existed, probably had the same ordinary days we have, the same politics, the same slow-moving debates about risks that seemed distant until they weren't. They were us. Or something close enough that the distinction doesn't matter from this distance. We are either extraordinarily rare or extraordinarily temporary, and either way, that changes how you should think about what we do next. We started with a simple question: where is everybody? And the honest answer is that we don't know. We've spent decades building larger telescopes. We've scanned billions of radio frequencies. We've pointed our best instruments at thousands of star systems and waited for a signal that never came. The mathematics says there should be civilizations out there. The silence says otherwise. And the uncomfortable truth is that after all the searching, after all the theories, after all the careful reasoning about filters and dark forests and cosmic zoos, we are no closer to a definitive answer than Enrico Fermi was when he asked that question over lunch in 1950. We simply don't know. That uncertainty is not a temporary gap in our knowledge. It may be one of the deepest and most permanent mysteries we ever face. What makes this particularly difficult is that every possible answer carries weight. There is no comfortable version of this story. If we are alone, that means the universe is almost incomprehensibly vast, almost incomprehensibly old. We are the only minds it ever produced capable of understanding any of it. That is an extraordinary thing to be. It is also an extraordinarily lonely thing. 13.8 billion years of stars forming and planets cooling and chemistry arranging itself. It produced exactly one civilization intelligent enough to ask where all the others went. If that's the answer, the universe is not empty by accident. It is empty by nature, and we are a statistical miracle so improbable that it may never happen again. But the alternative is worse. If life arises regularly, if intelligence is not rare, if civilizations form throughout the galaxy on a fairly predictable schedule, then something stops them. Something ends them before they spread, before they become visible, before they fill the cosmos with the kind of noise that an advanced species should produce. That something might be waiting for us. It might be something we are actively building toward right now without fully recognizing it. The fact that we have not detected a single long-lived interstellar civilization is not a neutral data point. Under this interpretation, it is a warning. It is the universe telling us, as clearly as silence can tell anyone anything, that the path ahead is dangerous in ways we do not yet understand. Most people don't realize how much hinges on a single discovery that we haven't made yet. Finding microbial life on Mars would be one of the greatest scientific discoveries in human history. The headlines would be extraordinary. The implications for our understanding of biology and the origins of life would be enormous. But under great filter logic, finding life on Mars is actually bad news for humanity's long-term prospects. If life arose independently on two planets within the same solar system, then life arising is not the rare event. It is not the filter. The filter is somewhere further down the line, and the further past us that the filter appears to be, the further ahead of us it must lie. Finding complex multicellular life elsewhere would be worse. Finding intelligent life would be the most alarming discovery in the history of science. Not because contact with another civilization would necessarily be dangerous, though that carries its own set of problems, but because it would mean that intelligence arises relatively easily in the universe, which means the great filter almost certainly lies ahead of us, which means civilizations routinely reach our current level of technological development and then fail to survive it. Every positive discovery about the prevalence of life in the universe tightens that logic. The silence we hear right now is uncomfortable, but it is the silence we should probably be hoping for. There is no resolution waiting just around the corner. This is not the kind of scientific question where better instruments will deliver a clean answer within a generation. The James Webb Space Telescope can analyze the atmospheres of exoplanets for biosignatures. Future missions may search the subsurface oceans of Europa and Enceladus for microbial life. Radio arrays far more powerful than anything we have built are being planned and funded. Each of these represents genuine progress. Each of them could, in principle, produce a discovery that reshapes everything. But even if we find microbial life on a dozen worlds, that still doesn't tell us whether intelligence is common. And even if we detect a radio signal from another civilization tomorrow, that still doesn't resolve the question of whether it survived. The Fermi Paradox is resistant to clean answers because it sits at the intersection of biology, physics, astronomy, game theory. The deep history of a universe we can only observe from one position, at one moment in time. We are looking at the cosmos from a single planet, at a single instant in a 13 billion-year story, through instruments that can only detect a narrow range of what might be detectable. Our observations are incomplete in ways that are difficult to even fully characterize. We might be missing signals that are there. We might be misinterpreting natural phenomena as silence when they are actually something else entirely. The honest scientific position is that we have searched very little, and we have found very little. Those two facts are not yet in contradiction, but the absence of obvious, unmistakable evidence from advanced civilizations is itself significant. A species 1,000,000 years more technically developed than us should have had time to reach every star in the galaxy many times over. The energy output of a civilization building large-scale stellar engineering should be visible across enormous distances. We're not looking for something faint. We're looking for something that should be, by any reasonable expectation, impossible to miss. And we miss it every time we look. That is not easily explained away by incomplete surveys. Something about the universe is genuinely not producing the kind of signal that the Drake equation's more optimistic estimates would predict. Some scientists think the answer is simply that we overestimate the probability of intelligence, The gap between simple chemistry and a species capable of radio astronomy might be so improbable that it happens once per galaxy or less. The universe might be full of bacteria. It might be full of complex ecosystems even. But the final step to a civilization capable of technology might require such a specific combination of conditions, sustained across such an improbably long, stable period that it barely ever happens. Under this view, the silence isn't terrifying. It's just the universe being what it is. We happen to be an exception so rare that the word rare doesn't really capture it. Other scientists find that implausible. Life on Earth moved from single cells to complex animals relatively quickly once the conditions allowed it. Intelligence and tool use appeared in multiple lineages independently. The trend of evolution on this planet, given stable conditions, seems to push toward increasing complexity and problem-solving capability. If that trend is general, if it applies to life wherever life arises, then intelligence might be the rule rather than the exception, and then the silence becomes very hard to explain without invoking something that ends civilizations. Both camps have reasonable arguments. Neither can currently prove their position. The paradox holds. What we can say with confidence is that we are at an unusual moment. We are old enough as a civilization to ask the question. We are technically advanced enough to search for an answer, but we are not yet advanced enough to have found one. We exist in the window, the brief period between developing the capacity to look and developing the capacity to actually see clearly. That window might be a few centuries long. It might be shorter. The question of whether we survive long enough to find the answer is not entirely separate from the answer itself. If the filter lies ahead of us, the civilizations that reached this window before us did not make it through. We are right now in exactly that period. Building better instruments is the right response. Sending probes to Europa is the right response. Continuing to scan the radio spectrum is the right response. These are not futile gestures. They are the only way the question ever gets answered. Each generation that passes the search along to the next, with better tools and sharper methods, moves us incrementally toward clarity. And clarity, even if the answer it delivers is uncomfortable, is worth having. The alternative is to stop asking. That has never been a serious option for the kind of species that built telescopes in the first place. The theories we've explored, the rare Earth argument, the great filter, the dark forest, the zoo, the simulation, the detectability window, are not equally likely. Scientists weigh the evidence and lean in different directions, but none of them can be ruled out with our current knowledge. All of them remain live possibilities. The universe hasn't told us which one is right. It has told us over and over again in every direction we point our instruments that it is not going to make this easy. The silence is consistent and deep, and it is held across decades of searching. That consistency is itself a kind of data. It is telling us something. We just don't yet know what. The first sentence of an answer might come from a mission already launched. It might come from a telescope being assembled right now. It might come 100 years from now, or 1,000, or never. The Fermi Paradox might be one of those questions that outlasts the civilization asking it, which is, under some of the darker interpretations, exactly the point. We keep building bigger dishes. We keep refining our models of where to look and what to look for. We keep funding the search because the question demands it. This was because something in the human mind, once it has understood the scale of the universe and the depth of the silence, cannot simply let it go. We keep listening, and the universe keeps not answering, and every year that passes, the silence grows a little heavier.